Thank you, Devendra. So as Devendra already has mentioned, in the next version of Mathematica, we'll have quite significant performance improvements in polynomial algebra. And those performance improvements are mainly based on the FLINT library that we are now using. So let me talk more about this. So the FLINT library provides efficient implementations of polynomial algebra algorithms within a fixed polynomial ring. So the available rings are univariate polynomials in dense representation, multivariate polynomials in sparse distributed representations, and the coefficients domains can be integers, rationals, integers modulo p, with separate implementation for machine-sized integers and big integers. So the main gain we are getting here comes both from using specialized algorithms that may apply to a specific type of problem, and for recognizing the specific polynomial ring and doing the whole computation within this polynomial ring rather than within the ring of polynomials with arbitrary expression coefficients. So using special data structure to represent polynomials within a given ring, that's what gives a lot of improvements, even if the algorithms used by the library are the same algorithms we have implemented in Mathematica. And the library also provides linear algebra functions for matrices of univariate polynomials over the integers and over the integers modulo p with machine-sized p. So these are the cases that library handles, and these are the cases where we get really large improvements, especially in linear algebra, where now we have special algorithms for matrices of univariate polynomials over the specific coefficient ring, as opposed to matrices with arbitrary symbolic coefficients. That was the kind of algorithm we were using before. So having the specialized algorithm for matrices of univariate polynomials gives us a lot of speed up. So we have direct improvements in this function listed here. So direct improvements means that basically the whole computation can be done by the FLINT library function. Of course, for the cases that can be handled by the FLINT library functions, and cases where the FLINT library is actually more efficient than our Mathematica internal code, it's not always. So we picked the cases where it was faster. And but for those functions in cases where they apply and where FLINT applies and is faster, we can just do the whole computation with FLINT. Now, indirect improvements means, well, these are the functions that use the directly improved functions for most of its computation. So for instance, polynomial LCM and together are basically using polynomial GCD for most of its computation. Discriminant uses resultant. Subresultants, that's more complicated. So there is no implementation of subresultants in FLINT. But we are using now FLINT for coefficient arithmetic within our own implementation of the subresultants algorithm. Similarly, polynomial real root isolation. We use FLINT for the Taylor shift. So that's transformation of f of x into f of x plus 1. For the polynomial, it's used all over the place in real root isolation. And so just improving this part gives us about factor of 2 improvement for polynomial real root isolation as a whole. And well, all symbolic computational functions use polynomial algebra, so we will get some speed improvements in most of them. For the cases where the problem will use the polynomial algebra over the integers or integers modulo primes. Okay, and now we also have a couple of functionality extensions in addition to speed improvements. So factor now works for multivariate polynomials over ZP, over integers modulo P. So we expand polynomials with modulus 2, and we can now factor it back over the modulus 2. So in 13.1, we would get the message that we cannot factor multivariate polynomials with respect to non-zero modulus, and it will use factor square free. In this case, the polynomial is square free, so nothing will happen. And the other improvement, also for the modular case, this time in linear algebra. So linear algebra, all those functions that inverse linear solve, row reduce, null space, and matrix rank now work over ZP for matrices of univariate rational functions. So before that, all those functions will complain that, oh, here it is. So in 13.1, you would get something that basically, if the matrix involves symbolic stuff, you would get a message saying that it's not valid modulo prime, or slightly better message was for linear solve. It was saying that the option modulus may be specified only for integer and rational matrices. So that actually is a nicer explanation of what was happening. Basically, only integer and rational matrices would work with non-zero modulus. And now we can do linear solve for matrices of univariate polynomials, and let's check that this really is a solution. And also we can do, for instance, determinant for actually, we can have even multivariate rational functions in the case of determinant, and it works. This is the determinant. You have to believe me. I'm not checking this, but 13.1 was not finishing this, not computing this correctly at all. So let me now show some performance comparisons. So all those plots will look pretty much the same. So the timings are on logarithmic scale. So, and we get the actual speed improvement factor here in each part of the plot. So it's, for instance, here it's for dense univariate polynomials of degree n, we take product of two polynomials such that the GCD has degree n. And if n is 100,000, we get a speed up factor of 1,300. So as you can see, this looks like the new algorithm used the implementation of polynomial GCD in FLINT has better complexity, so because the speed up factor is growing. Now same thing now for bivariate polynomials of total degree n. We have a certain number of terms, and all the coefficients have 10 bits. And now we have slightly, or not as big improvement as we did for univariate case. The best improvement is measured is by a factor of 16, but it's still nice improvement. Now same thing for univariate polynomials modulo a prime. So for the prime, we take prime of 1, 2, 3, 4. It will also be used in all the other comparison. We use the specific prime. And as you can see, the improvement grows with the size of, with the degree of the polynomials. You also get better complexity. Best measure factor is 332. And again, for multivariate polynomials, so we take bivariate polynomials, the improvement is not that large, but it's still improvement across the board. The best measure improvement is factor 8.8. Now resultant is slightly slightly more complicated. So for univariate resultant, we use the FLINT library, and we get improvements from 2.1 for degree 10 to best measure is factor of 10 for degree 2000, for degree 5000, 13.1 implementation runs out of memory, so we don't get this data point. For multivariate polynomials, here we have bivariate polynomials. The situation is more complicated in the sense that the FLINT library implements only polynomial remainder sequence method for computing multivariate resultants, and in most cases this is not the fastest method. So we still get improvement here, but the improvement we are getting in this example comes from using our old algorithm, modular algorithm for computing the resultant. But each modular case, that subcase generated from this modular algorithm, the modular algorithm computes the resultant modulo a bunch of primes and then uses Chinese remaindering to get the resultant over the integers. And so now the modular cases are sent to FLINT library, and they are faster by about a factor of 5 probably. It's the same algorithm. It's probably the factor of 5 is due to just using the more efficient data structure that's specific to polynomials over machine-sized integers, modulo machine-sized prime. So that's where we get pretty much constant factor of 5 improvement. And this is the multivariate modular. Here we get, so first we get about factor of 2 or even slightly less improvement, and then this is where our algorithm was switching the automatically chosen methods, and apparently the methods that are chosen for higher degree are much slower than what we get with FLINT. So the speed improvements go from about a factor of 2 to a factor of 500, 2000 here almost. Oh, actually, this were the univariate case. And we have the same picture for multivariate case. So for lower degrees, about a constant factor of 5. For higher degrees, there is an algorithm switch in 13.1 that the algorithm becomes really slow, and we get a factor of infinity, which infinity here means that we didn't compute the result in 10,000 seconds. All the examples here have 10,000 second bound on computation. So if we get a row like this with infinity here, that means it's more than 10,000 seconds. Okay, now factor square free improvements. So we do sort of minimal non-trivial square free factorization. So it's p times q squared. We randomly select p and q of degree n. And again, for the univariate case, we get better complexity. For the highest measured speed up is by a factor of 1200 for polynomials of degree 50,000. Now, bivariate polynomials, again, similar pictures before, slower speedups, still speedups. For degree 500, we get this largest measure speedup of factor 8.5. And the same thing now over the modular domain, so over prime modulus. We get, for the univariate case, we get slightly smaller speedups than before. The best speedup is by a factor of 30. Actually, it drops for higher degree. And here is the bivariate polynomial case over prime modulus. Again, the largest speedup that we are able to measure is 46, factor of 46. factor performance improvements. So we take product of two randomly generated polynomials. So here is the univariate case. Again, growing speedup factors. The best measured speedup factor is 800. Here are trivariate polynomials, and in the case of factor, actually, we also get a very large improvement for the multivariate case, large and growing improvement factors. So highest measured factor is 572 for 46 degree. Oh, these are sort of evenly spaced on the logarithmic scale. That's why we have degree like 31 and 46. And here is a factor modulo prime modulus for the univariate polynomials. And factor is growing, but the best measured is for degree 2000. It's a factor of 46, so not as large as for polynomials over the integers. And we don't have the fourth plot where we would have factor of multivariate polynomials modulo prime modulus, because in version 13.1 it was not implemented. So the FLINT-based implementation is the only implementation we have. Now, matrix power performance improvement. So now we go to linear algebra. So we have a 10 by 10 matrix of randomly generated univariate polynomials of degree 10. And we are varying the power, the exponent. And as you can see, the speedup factors vary from 0.2 to 5,600, the best measured ones, and for higher degrees, the version 13.1 times out. But this is not the whole picture. It's why do we keep something that's actually got slower here? It's slower by a factor of 5, so from probably about 1 millisecond to about 5 milliseconds, but it's slower. Because the old version was not doing any simplification. It was just producing the power of the matrix with multiplied out and added symbolic coefficients, symbolic entries of the matrix, and so the size of the result was growing dramatically. So now let's look at leaf counts of the produced results. So already for exponent 2, we have, it's 5 times slower, but the resulting leaf count is 10 times smaller, because we get the matrix of expanded polynomials, so we get the minimal leaf count. And as you can see, the leaf counts were growing dramatically. So the largest computed thing, we have a leaf count improvement factor of 6.6 million. So the old result had 1.6 trillion leaf count, actually. So that's the largest expression I've ever seen actually computed. Computing the matrix power took about 1 hour. Computing the leaf count took 8 hours. So it was really huge. And of course, when it comes to using it in further computation, if we get something with some unexpanded huge thing, we cannot really use it in further computation. So that's why, even though we may get slowdown for small exponents, we are still using the fully expanded version in 13.2. Okay, so now let's compare performance of determinants. So here is determinant for n by n matrix of randomly generated univariate polynomials of degree 10. So we vary the size of the matrix. And the speed improvements goes from about factor of 8 to about factor of almost 90 in this range of sizes. So that's for 70 by 70 matrix, and it's the largest matrix that we can actually deal with in less than 10,000 seconds in version 13.1. Let's look at inverse. That's an interesting thing. So we take n by n matrix of polynomials of degree 10, and it seems that the largest speed improvement is for a 10 by 10 matrix, which is factor of 786, then the factor drops off to around 100 something. The infinity here doesn't really mean that it's more than 100 something, because it's 116 in the new version, more than 10,000 in the old version. Linear solve improvements, also similar picture, factor of 240 for degree 10, then it stabilizes at 100 something. Very similar pictures for row reduce. This time the best factor is for degree for 5 by, or it's actually 5 by 8 matrix, because we want the row reduce to be slightly non-trivial. So we take n cross n plus 3 matrix, and then the speed up factor stabilizes at about 150. And null space, very similar picture, also stabilizes at about 150, 140. And matrix rank improvements. So here also large factor for slightly smaller matrices, like 5 by 10, because it's n by 2 here. And then it stabilizes at around 20. And here is last example. It's an example of indirect performance improvements. So here we have solve values. We actually didn't change the code of solve values itself, but it's using polynomial factorization and real root isolation to produce the roots of the Chebyshev polynomial of degree 1000. And in Mathematica 13.2, it's, well, it took no idea why it takes 14. Well, last time I tried, it took 2 seconds anyway. In Mathematica 13.1, it took 30 seconds. No idea why absolute timing is so large. Today, maybe my computer is doing something. Okay, so that was it. Thank you for listening. And if there are any questions, I will try to hear them through the microphone. Let's see how it works. Thank you.
Thank you, Adam. If we have time for maybe one question, if there's anything that you... Yeah, and yes. Adam, maybe we can stop sharing so Tigran can start sharing then.
Okay.
What was done with apart to improve speed apart?
Good question. Adam, the question is, what about apart? Any change apart with your improvements?
Well, apart is using factor, so I would expect apart would become faster.
You should test it. Maybe.
There was no direct change to apart, but as long as apart is using factor and GCD, there will be some speed improvements there.